In this video, we're going to continue with stoichiometry, and we're going to take a look at some more specific examples with ratios and move into stoichiometry in more detail. In the last video, we saw ratios and an introduction to stoichiometry and related it to some kitchen chemistry. So we are going to do some examples with this equation over here. We're going to write a mole ratio for this equation between Al and AlCl3, and then try to use our mole ratio to try to solve some problems related to stoichiometry. And same thing for Al and HCl. So there's a little bit of a trick here. It's called a conversion factor in dimensional analysis. This is a way you can show your work. Essentially what you do is you take the moles of the known stuff, the stuff that you know, multiply it by the ratio that you create, where you have the moles of the unknown, what you're looking for, and the moles of your known at the bottom, so the known can cancel out, and you get moles of unknown left over. That seems confusing when I say it like that. When we do an actual problem together, it'll make more sense. So this is your ratio that you create using your balanced equation, and this is the moles given to you in the question. Let's go take a look at how that works. Let's go to our handout over here and take a look at the chemical reaction. So first of all, let's make sure we balance our reaction. So we have a chemical reaction here and we want to balance it. So it looks like I need, okay, I think I'll put a 2 here. That'll give me 6. A 3 here, a 6 here, and a 2. And I think it is the simplest it can be. So that is balanced. And we're going to write a mole ratio between aluminum and aluminum chloride. So between Al and AlCl3. And so we have 2 Al for every 2 aluminum chloride. In other words, it's a 1 aluminum to 1 aluminum chloride ratio. You can also write it as a fraction. For example, 1 Al for every 1 AlCl3. And I could have said mole or molecule. So 1 mole of Al for every 1 mole of AlCl3, or 1 molecule of Al for every 1 molecule of AlCl3. You could also write it the other way around. If I asked you to write a ratio, I would have actually worded it, write a mole ratio for AlCl3 to Al, but again, you could write it this way as well, 1 AlCl3 for every 1 Al. And why you'd want to use one or the other, it'll make more sense once we actually do the practice problem over here. So notice that if we want to make 2 moles of AlCl3, we need 2 moles of aluminum. We're ignoring the HCl. It's going to be there. We're assuming we're reacting that in good amounts, but we need 2 moles of aluminum. So it's a 1-to-1 ratio. If you have 2 Al, you have 2 AlCl3. If you had 3 Al, you'd have 3 AlCl3 because they exist in a 1-to-1 ratio. That's how the recipe is going to work out. So in your head, you can already probably figure this out. If you had 4 moles of aluminum, Al, how many moles of aluminum chloride should you have? Based on the fact that it's a 1-to-1 ratio. And it follows that ratio all the time. So you're probably already thinking, okay, I should have 4. And that's right. That is correct. That makes sense. Let me show you how you would solve that, though. So what I do is I do the number of moles given to me in the question. So 4 moles is what I'm using in the question of aluminum. So 4 moles of aluminum, I'm going to put that there. And I'm going to multiply it by a ratio, including my unknown over here. The ratio has to be between what I'm given in the question, so aluminum, and the unknown. And the ratio is made by the coefficients of those. So, it's a 2-to-2 ratio between them, which is what we found over here, or a 1-to-1 ratio. So I'm going to multiply it by that ratio, but I'm going to multiply it by the ratio that will get rid of aluminum and leave me with aluminum chloride. So that means I'm going to do the, that should be a 3 there. I'm going to do this one over here. Nope, that won't get rid of aluminum because aluminum is on top there. So I'm going to choose this one over here because aluminum is on the bottom, and when you have units on the bottom and top and multiplying, they'll cancel each other out. So I'll do times the 1 mole, because we're dealing with moles now, of AlCl3 over 1 mole of Al. And so I can cancel out mole of Al, and I'm left with moles of AlCl3 there. So I'll get 4 moles of AlCl3. In a multiple choice question, or a question where you have to go pretty quickly, you can just say, okay, it's 1-to-1, right? So you can say that it should also be 4 moles of AlCl3. So you can write 1 to 1, therefore 4 moles of AlCl3 should be produced with 4 moles of Al. Okay. So let's try another question. Let's do the mole ratio for aluminum and HCl. So here's aluminum, here's HCl. It's a 2 moles or molecules of aluminum for every 6 moles or molecules of HCl. And you can reduce that to 1 aluminum for every 3 HCl. You can also write it as a fraction. So for every 1 aluminum that you have, you'll have 3 HCl's reacting. Or for every 3 HCl's reacting, you'll have 1 aluminum reacting. So the ratio for the ingredients exists there too, right? It's like saying if you want to make a grilled cheese sandwich, 2 pieces of bread and 1 cheese makes 1 grilled cheese sandwich. You have 2 pieces of bread for every 1 cheese. It's always going to be, so you can have ratios between those reactants as well, those ingredients. So let's use our ratio to try to solve a problem like we did in the first case. How many moles of HCl would be required to react with 6 moles of Al? So let's look at our ratio. Let's just think about it before even writing anything down. We know it's a 1 to 3 ratio. We know if you have 1 aluminum, you'll have 3 HCl. So if you have, in other words, you have 3 times more HCl every single time. So if you have 6 Al, think about that in your head. Okay, I need 3 times. I'll probably need 18 HCl because that will maintain my 1 to 3 ratio. I have 3 times more HCl every single time compared to the Al. But let's write that down using our unit analysis there. So in our question, it says how many moles of HCl would be required to react with 6 moles of Al. So I'm going to write my moles of my known, so 6 moles of Al, multiplied by one of these ratios here that will get rid of aluminum. And I think it's this one here because aluminum will be at the bottom. So 3 moles of HCl over 1 mole of Al. And so we're going to cancel out moles of Al there, and we're left with moles of HCl as 6 times 3 divided by 1, which is just 6 times 3 essentially. And so we get 18 moles of HCl. Just like you predicted in your head, you're able to use that mole ratio in your head to do that. And here we're just showing it with the unit analysis, dimensional analysis, and ratios. And that's how you would show your work. I know right now it just seems easier to just do in your head times 3 because it's 3 times more than Al, but eventually the ratios become a bit more complex, so it's easier if you can actually write it out, cancel things out, and apply it that way. So that's a basic example of creating a mole ratio and using it to solve a mole problem. This was a mole stoichiometry problem. It was a mole to mole problem. Nice and straightforward, except we broke it up into a few different parts to tell you, make your ratio first, then do this and that and the other. But that was what that conversion factor was also about in this slide. The moles of what you know in the question, what you're given, what you're actually working with, multiplied by your mole ratio to make sure you cancel out the known one and leave the unknown one that you're looking for there. And so we use that to solve our first stoichiometry problem, which was this one here. And now we're going to do like a real official one where we don't break it up in little steps like that, and I'll show you how that all works. So in our next video, we will go on to the next few examples of mole-to-mole stoichiometry. And hopefully you're getting more confidence with this topic as we broke it up into those individual skills.